Okay.
Welcome everyone. It is my great pleasure today to welcome Dr. Tim Starkey, who is a research fellow at the University of Exeter in UK, and Tim is going to talk about acoustic metasurfaces and their application to turbulent flow. So, Tim.
Take it away. Okay. Well, thank you very much, Sebastian, and thank you, Bogdan, for the introduction and for the opportunity to talk today. So unlike, I think, the list of some of the previous speakers would indicate, many of you won't know who I am. So for those that aren't aware, I was just going to say a few words about the stuff that we do at Exeter before moving on to the topic at hand. So I work in the Centre for Metamaterials Research and Innovation. It's a relatively new centre that we're trying to set up that spans quite a lot of topics in metamaterials. But there's been a centre or a research group for nearly the last 40 years studying all kinds of related phenomena. So way back in the day before I was born, there was a lot of research into thin metal films and plasmons. And gradually over the years, this has migrated to longer wavelengths, to microwave photonics. And now we do quite a lot of work in the acoustic space. So within the acoustics group, we kind of have a mixture of research areas. Some academics are looking at thermoacoustics. I work on quite a lot of acoustic phenomena related to surface waves and waveguides. We have people looking at energy harvesting, acoustic magneto interactions, and other 3D mesh materials and phononic crystals. So there's quite a lot of research going on. I joined the group about 4.5 years ago with a kind of broadly open remit to look at acoustic metasurfaces for use in air. I've done a bit of dabbling underwater, and one of the projects we've been looking at and working on over this time is trying to apply acoustic metasurfaces to a turbulent flow and see what can be done in that space. So the research I'm going to present to you today is done in collaboration with colleagues at Virginia Tech. So it's a really nice collaboration where in Exeter we're kind of more focused on the acoustic metamaterial side, and in Virginia Tech they have some absolutely phenomenal pieces of kit to generate flow and turbulent flow to do the experiments we want to do. So let's start with the problem, and hopefully can move across slides. No, I can't. There we go. So I think that the background or the opportunity can basically be summarized in this sentence. So surface structures can strongly modify the pressure field or the velocity field or whatever your favorite kind of field is that manifest above them. So in aerodynamics and the aerodynamics of turbulent boundary layer flows, surface treatments can have a significant impact on the sound generated from or the pressure fluctuations present within the flow and the boundary layer close to the surface. And I've included a nice picture here from the biological world, and that is the wing of a barn owl. So through millions of years of evolution and the selection pressures, the barn owl has developed really nice surface structures and serrations on its leading edge that enable it to fly very silently. So it has an aeroacoustic function, and it also flies with very little drag. So the two are kind of linked, the aeroacoustic and the aerodynamic properties. And engineers have looked to the biology to try and inspire some surface treatments, and there have been various surface topologies studied. So things like roughness noise, the noise that originates from having ordered fetches and certain canopies and porous treatments. So this is kind of a non-resonant phenomena usually, and the key thing is that the flow moves over a surface, and that it provides some kind of treatment and dresses the flow for some desirable effects. So coming from the opposite side, where I'm interested is acoustic metasurfaces. So I've just borrowed this nice figure from Schwarn et al, where they developed some theory related to metasurfaces. And basically a metasurface is exactly what it says. It's a It's a surface that comprises these metamaterial elements. So these are often small structuring, usually resonant elements, and they could be Helmholtz resonators, elastic voids, or membrane type materials, or some kind of labyrinthine cavity. And all of these can be used to generate neat acoustic features to modify the pressure field that interacts with them, whether it be a near field or a far field, for a range of applications. So I've again put these couple of quite vanilla applications, which is noise and vibration control. But clearly, if you've attended any of these webinars, you'll know there are absolutely tons of sort of fundamentally new concepts related to dealing with acoustics, but also metasurfaces are a really nice way of demonstrating certain aspects of physics that might appear from condensed matter and so on. So this is really the point. The point is these treatments, both in flow and metasurfaces, will respond to pressure fluctuations, and these could be evanescent pressure fluctuations. And what we're going to try and do is marry the two together in some neat way that we can design metasurfaces to control the flow. So I have to confess, it's been ages since I've given a real talk because of COVID, and this is one of those talks that I've not done before properly. It's we're bringing together two new ideas. The results are relatively new, and ordinarily the talk should do some incremental change. So I'm going to give you the outline and tell you what I'm going to try and tell you. Oh, move again. So the outline is basically, I'm going to provide some background because we want to treat the flow with some kind of surface. One neat way of doing that is to use an acoustic surface wave. This is a mode that's bound to the surface. I'm going to talk about some of the experiments we've done in a sort of quiescent environment where there's no flow. And then we're going to talk about how we go about applying a turbulent flow to these, the wind tunnel facility that we use to measure them, and to sort of give you some results based on two metasurface waveguides that we've designed. And then I'll finish up by telling you where we're trying to go with it. So since we're a largely metamaterial audience, this seems like a really nice place to start for sort of surface wave theory. So in 2004, there was obviously this really seminal piece of work by Pendry and co-workers, where they showed that you could texture a perfect electrical conductor, or basically a metal, and you could introduce a surface wave where you wouldn't ordinarily expect one for an unstructured or untextured substrate. So obviously the theory for just a plane of metal surfaces that you like silver or gold, you'll get a resonance called the surface plasmon resonance, which is related to the sort of polarizability of the electrons on the surface. And as you go down in frequency, you no longer have basically a surface wave, because the penetration of the field into the metal is non-existent. So this figure just describes what happens when you're at sort of lower frequencies. There's no penetration into the metal, and the electrons basically screen any kind of electric field into it. When you texture one of these surfaces, you introduce a resonant phenomena, and it enables you to localize the electric field at the interface between, here we're talking about air, and some structured metal. And this is all this is meant to show. It shows that you've got some decaying field in the air above and some decaying field into the metal. And all this really requires is these inclusions to have some cutoff frequency. And what you get is a beautiful sort of asymptotic dispersion. So this looks just like a surface plasmon, but it occurs at this asymptotic frequency, which you can design via the inclusions in your surface, or these little perforated inclusions. So the key thing here is that the surface wave, this thing out here that exists beyond the light line, has momenta larger than that of a free space wave. And as this kind of indicates by this decaying field, it cannot couple to free space radiation. So you can do similar things in acoustics. You can take a rigid surface with no texture, no holes, and you can start playing tricks by adding some kind of surface structure comprising resonators. So the analogy doesn't entirely work, because if I have a rigid surface, there's no sort of plasmon frequency, there's no surface plasmon, or I don't know what it would be called, like a surface acouston. Those don't exist. But what you can do is you can go to basically a rigid substrate, and you can mill a series of grooves in, which will act as a series of cavity resonators. So here, this schematic is basically meant to show I've got some acoustically rigid material, meaning that the pressure field will not propagate into it. This material totally screens it. I add a series of corrugations or grooves, and these grooves will support a resonance, which will be n multiples, in this case because of the rigid boundary condition of the quarter lambda Fabry-Perot condition. And if you get things right, if you have the right spacing and the right coupling between them, you'll get diffractive coupling of the pressure field between the resonator cavities, which will give you a mode of the system that exists beyond the sound line. So let me just demonstrate what these look like. So this is like kind of the background stuff before we get on to some of the experiments we've done. So for the simple grating, you have these two distinct regions, and I'll just spell this out because I know that in lots of talks we talk about just the wave number, and the wave number is simply the wave number as it propagates through the sample. Here it's slightly different because we're talking about the in-plane wave number, which is the projection of K0 onto the surface. So this dispersion map, this wave number frequency space is split by the sound line. So this is just a grazing sound line across the surface. You can think of this as a wave that's just moving parallel to the surface. To the left of that, you've got the radiative regime, where you can couple to it with plane waves. So here, if I go up at k equals 0, this is me sending in a sound wave at normal incidence, and then basically taking the reflection. And every time I come out here, this will correspond to an angle off normal until I eventually get to 90 degrees, which runs down the sound line. So here what we're seeing is a resonant mode, which is just the fundamental resonance of the cavity. And in reflection, this reduces the reflection from what would be 1 for a perfectly rigid solid to about 0.65. And this arises due to thermoviscous losses in the cavity. Now on the non-radiative side, we can run models and look at the eigenmodes for the non-radiative case. And what we get is this modal system that begins at, oh, there we go, where has it gone? Begins at 0 frequency, disperses along the sound line, and as it approaches the resonant frequency of those cavities, it asymptotes off and approaches the Brillouin zone with 0 group velocity. So the gradient of this thing gives you the group velocity. And obviously there's some key points in this dispersion plot, and probably the most important is the Brillouin zone boundary here, where the wavelength is equal to twice the pitch, and we get a Bragg scattering condition and a standing wave where there's no power being propagated along the surface. So this is nice. What we're interested in these bound modes, and you probably guessed that by changing the cavity depth, you can, or changing the kind of spacing between these cavities, you can change the coupling between them, and you can start pulling this thing down. This is usually a effect of a depth, or you can start changing the way this pulls off the sound line by the intercavity coupling. So this is meant to give you the full picture. So that's both of them together. And what we've been doing in Exeter is taking really simple structures, basically drilling holes into them and studying the modes that are supported by them. So one of the simplest cases you can take is to take a line of cylindrical boreholes. In this case, what we have is a perspex sheet, which for the frequencies we're looking at in air is essentially a rigid object. You can mill cylinders all the way through them, and these will support a series of resonances which look like half lambda organ pipe modes. And you can do exactly the same as we just previously described. You'll get a dispersion relation, which is due to the coupling of the cavities, and they just couple along the line, and you get a wave that's supported along them. So in this experiment, what we do is we put a source in one hole, And on the other side, we just map the temporal response when we send a pulse into the loudspeaker as a function of space. And using Fourier analysis, we can obtain the surface mode dispersion, and we can also construct and show what the pressure fields look like on the surface. So this is just one example here. So we've got the little red dots indicate the results of the numerical model, and these basically agree really nicely with the color data beneath, which is actually obtained from the experiment. And what you can see is, just to really spell it out, for the low frequency pressure field, which is taken along this line here, you have a mode that's dispersing. It's very close to the sound line, and you get a bound mode that propagates along the sample for quite some distance. So we're going up to nearly 600 mil here. As you come up in frequency, the group velocity of the mode is slowed down. This thing doesn't propagate quite as far, because with lower velocity, the thermoviscous losses in the cavity begin to play a more significant role. And when you finally start to get to frequencies close to the asymptotic frequency of the cavity resonance, the surface wave is propagating with virtually no distance. And in fact, here you can see there's some odd beating that's occurring because we've got a source placed in a hole here. Sound is bouncing off the end here because the impedance mismatch, and we're just getting a kind of illusory beating that makes it look like it's traveling the wrong direction. So you can take these simple cavities, you can arrange them in a line, and you get a surface wave. So this is one bit of experimental work we've done, but you can also begin to tailor these in different ways by changing the arrangement of your resonators. You can start to add additional structure factor into your unit cell. You can and introduce more modes of the system. You can also look at systems where you have different symmetries, and providing that you've got sufficiently well coupled resonators, you can play with these to no end. So one of the studies we've done is to take these acoustic surface waves around arbitrary paths. So here we've got a circle of cylindrical holes. Yeah, equally you could have just taken a random S shape or whatever you happen to like, whatever shape you like, and you can do the same experiment. So here we've got a source, and we excite and measure the field around this ring, and you see that you get the same kind of mode dispersion. Here we're talking about like a circumferential wave vector, but it's totally analogous in its behavior. The only difference actually in this one is that you can get some radiative losses, which you don't get in the line, and these are proportional to the radius of curvature. And kind of the intuitive reason for this is, as these decay away from the surface, there'll be some point at some radius where these can couple to something that will look like plane waves. Okay, so with all this in mind, you can also look at structures with greater symmetry. So you've got here a square array. In the square array, there are a number of different symmetry points. So there's gamma in reciprocal space, X, M, and we've fully mapped the dispersion on these structures. And just by virtue of having a square array, you can introduce some interesting features where, for example, at one frequency, so it's down here, you can have a wave supported that propagates in all directions on the real space lattice. So here we've got a source in the center, and you've got waves propagating out in all directions with pretty much no preferential direction, that are bound and traveling slower than the speed of sound in air. And then you've got situations where the mode no longer exists from, say, for example, here gamma to X, and you can get beaming, or here we've got fourfold beaming, which is just related to the symmetry of the lattice. So this is I've kind of included these slides just to show, hey, you can just take a relatively simple material, drill some holes in it, and you can support a surface wave. And as I said in the beginning, what we were interested in doing is seeing if we can couple these to a turbulent flow. So for those that don't know anything about turbulent flows, don't worry, I'm relatively new to it as well. But this slide is just to give a kind of a brief background to it. So if you have a fluid moving over a rigid wall, so in this diagram here, I've inserted some flow through this nozzle. Due to the no-slip condition at the wall, there'll be a layer where you get significant viscous effects, and you get these characteristic velocity gradients of the velocity in the flow, particles in the flow, above the wall. So this is kind of I've included this diagram below to show that it's kind of a horrid mess. This thing is meant to show like the coherent vortical structures as they propagate across the surface of the plane. And if you actually do the analysis of the wave number frequency spectra that exists within this turbulent flow at the wall, you get something that's very similar. And I was surprised because all of my knowledge about fluid flow was kind of stopped at undergraduate until we looked at this. You get structures that don't look dissimilar to that we see in the dispersion relation for an acoustic surface wave. So namely, that is, you get some sound lines. So this diagram on the right just maps the frequency wave number dispersion. So you get sound lines, and here it actually forms a cone because we're in this 3D space. So within there, that's your supersonic region, which I would call the radiative region, where I can couple sound to some plane wave. And then at momentum larger than that exists outside the acoustic cone, you actually get this subsonic region where there's this structure called the convective ridge. And this describes all of the evanescent pressure fluctuations that are non-propagating, not coupled to sound, that exist within the flow. So if we want to try and target this in a turbulent regime, what we need to be mindful of is that we want to basically interact with this region in the convective ridge. So the colors just indicate the sort of magnitude of those fluctuations. And this is the problem. So sort of the objectives of this work are to demonstrate the excitation of acoustic surface wave primarily. So drive one with these evanescent pressure fluctuations, measure the structure of these, and then demonstrate that we can tailor the acoustic surface wave towards some kind of flow application, whether that be absorbing energy, harvesting energy, or somehow reintroducing an acoustic wave to have some influence on the flow. So the experimental idea basically is that we can have, so this is like the deterministic experiment. This is what happens, or what we'd normally do in the lab without any kind of flow, is we have some kind of metasurface in a rigid material. We'll place a speaker in a hole that's basically a through cavity to the metasurface side. This cavity will support a resonance, and then we hope that sound will diffract out and basically couple to the surface wave, which we can detect on the other side. So yeah, sound is diffracted through, and by moving a probe and knowing when we trigger, say, a pulse from the microphone, we know everything we need to know to map out those full dispersions, and that's what we showed that's what I showed at the very start. In the flow case, things are a bit more complex in terms of you want to interface the turbulent flow on one side as my driving source, but I don't want to introduce any kind of additional undesired effects related to making this cavity, making it rough or adding discontinuities. So the way that we've decided to overcome that is to use a Kevlar screen. So this thing is essentially an acoustically transparent membrane, and this thing should basically allow any near field pressure fluctuations in the flow to propagate through, excite our cavity, and excite our surface wave in exactly the same way. But the other key difference probably in this experiment is we have to use a pair of microphones. So the stochastic nature of the source means that we have no idea about the field that's pumping this above. So to do our measurements, we need a fixed reference microphone and a traversing microphone. And if we do some smart analysis, we hope that we can pull out the surface wave from any other muck that's going on. So towards that, we designed a couple of different surfaces, and these have different surface mode dispersions for a couple of different applications that we've got in mind. So the first sample that we considered is simply termed the slot array, and this is just, it's very similar to the cavity of cylindrical resonators, except they're elongated as slots. So this top figure here on the left just shows you the bottom snapshot as if you were looking from the metasurface side. And what we have is we have our Kevlar through cavity to the flow side, which is this guy. And then the adjacent cavities are these quarter lambda resonators that we have basically tiled either side, and they're arranged so that they're actually along the streamwise direction of the flow. The choice of this elongated cavity basically arises from the fact we can target the spanwise wave number very nicely. So because of the flow we're introducing, we expect kind of near uniform spanwise behavior in the pressure fluctuations in the flow above. So it will help us couple strongly to the mode. And the other thing that's important about this design of this surface is that the plate heights and the underside metasurface heights or lengths of these simple acoustic resonators are designed in such a way that you have a lambda by 2 resonator down the center cavity, and you have lambda by 4 resonators in the adjacent cavities. And in that way, getting the heights right, you can overlap the frequency content of both modes, and you hope that your overlap integral is non-zero and you'll get some efficient coupling into the surface wave. So that's sample number 1. The second sample we've looked at is a meander array. So it's exactly as it sounds. When you look from the top surface, it just looks like we've sort of routed out, we've just milled this meandering cavity into our rigid solid. So this goes in both ways again. The flow is introduced in exactly the same way through a through cavity through the plate, and in cross section it looks nearly identical to the slotted array. And the reason these are chosen is because they have quite different dispersion relations. So for the slot array, you get something that looks really, really similar to the resonant cylindrical cavities that we were considering. You get modes start from 0 frequency, they come up the sound line and they asymptote to the fundamental resonances of the cavity. So for example, here we're just looking at an instant in phase at the Brillouin zone, and we have, you know, positive pressure, negative pressure type standing wave behavior. And you get the same behavior for the higher order modes. In this system, you also get quantized modes in the lateral width. However, due to the excitation conditions that I'll talk about in a minute, we don't really expect to excite those. And also due to the way we're going to measure it, we wouldn't expect to measure them. So I'm just showing the first 3 sort of fundamental modes quantized in the depth. For the meander array, we get kind of, at first glance, it looks really similar. The modes come up the sound line and then they begin to disperse. However, these things don't disperse to a fundamental resonance as they do in the slotted array. So this mode is just plotted up to the first Brillouin zone. And if there's anyone in the audience that knows about the symmetry of these systems, we could have a debate about what you call the first Brillouin zone. But for the sake of this talk, I'm just plotting it up to the first Brillouin zone of the unit cell shown. And what this system has is a particular symmetry operation called glide symmetry, which is where you can displace the unit cell by half a period and flip it, and you end up with the same structure. And this magic symmetry operation gives you this very broadband linear dispersion region where we can excite surface modes over a broad band. And this is the key purpose of choosing this one. So not only will it not disperse to a 0 group velocity, which will be good for our applications or some of our applications because the attenuation won't be so high, but it also means we get the broadband nature, which is cool. The theory of this mode dispersion is published by one of my colleagues in APL, and this is just a plot I've nicked from his thesis, and it basically shows that the dispersion relation of this surface or this meander waveguide has a pair of terms. One is related to the path length and one is related to the depth. So the path length here basically changes the distance this wave will have to propagate in the waveguide. So it wants to go this way. However, if you make a very long path, this thing is traveling an awful long, huge path length. So the apparent surface wave speed goes very low for very large h here. So you can bring it down here. And also it's defined by this depth term, which will determine where this thing begins to pull up a sound line. So it gives us a degree of control over the surface dispersion for our flow application. So those are the metasurfaces we would like to test. And to test them, we're using an experimental facility called a wall jet. So the wall jet is kind of a very controlled way to achieve a boundary layer flow. It mimics lots of the flow dynamics that you'd expect for a free field flow interacting with a solid object. I'll talk you through this one because there's a lot going on here. So on one end, what we have is we have a massive fan that inputs air into this settling chamber. The air moves around this series of baffles, which are acoustically clad to basically remove any facility noise, any noise from the fan that's present within the flow that's being convected down in the facility. It then reaches a series of chambers which try to settle the flow, essentially a series of meshes which straighten it out to reduce mixing in the span-wise direction. You maintain basically nice flow in the streamwise direction. And then this flow is brought up to it's contracted into a nozzle. So at this nozzle, we insert flow onto a wall jet. So the jet essentially expands into this large cavity and diffuses into a static environment, creating a turbulent flow in a controlled way. So along the surface, this is a rigid wall, you get the boundary layer, characteristic boundary layer, where the velocity is low at the wall, it expands due to the competing boundary conditions, and then the velocity goes low as you expand into this large volume of air. And some way down the test bed sample here, we introduce our metamaterial sample to study the excitation from the flow. So this is kind of what the test plate looks like. This is the nozzle. Flow comes through here, and then midway down, we have this sample mount that we can remove from the test bed. We can place our metasurface into it. We can interface it with our Kevlar. And then on the underside, down here, we do our measurement of the acoustic surface wave. And I've just included a couple of figures just to show you what this looks like. So this is what the wall jet looks like as you look down. So the flow is actually coming towards you here. And this is just a zoom in of our little Kevlar covered through cavity and the big test plate. So the only other thing that's worth pointing out is that the flow in this facility is silent. There are no sort of quadrupole terms for the regime we're looking at. So the only kind of acoustic contaminant comes from the facility noise and the thing generating the flow, or the air conditioning, or whatever else is going on in the room. So that's kind of the flow. And now we want to do some measurements of our metasurfaces. So our metasurfaces are basically printed in ABS. We sandwich them between these two plates and then drop them in to the wall jet, as we've just seen. Flow comes over the top. We've got this little through cavity like mouthpiece that's got the Kevlar on. Flow is going to excite this. And then on the underside, through the middle of the metasurface, we fix a reference microphone, and then we measure the traversing one to map out the pressure field as a function of space. So to obtain our acoustic information, we record the temporal response as for 8 seconds. We reduce the data using cross-correlation techniques and binning, and the data that I present is basically the auto and cross-spectral analyses between the two microphones, and this gives us a spectral estimation that we can use to obtain the surface mode dispersion. is kind of a smart Welch analysis for those that know about those things, except you have to build in the cross-spectral element between the two microphones. So all the method is described here. So moving on, this is some of the first data we see. This is the raw data, if you like, a snapshot of what's going on the metasurface. So what we have here, we've got the pressure autospectra, which is essentially the spectral estimation of the microphone that's being scanned across the surface at a series of points. So 0 is the through cavity, and then this is different points as we go downstream. We've plotted on here the wall jet pressure spectrum, if you to have a microphone mounted in the wall at that same position as a reference. And what we see is, for the metasurface, the levels come down a bit, or quite a lot actually. And as we go along the sample surface, we see that the levels generally decay across the whole frequency band, except for at specific points which are specific to the quarter lambda and 3/4 lambda resonances. So how we read these is where the intensity drops off, bear in mind it's on a log scale, there's not very much interesting physics going on. However, where you get grouping of intensity, like we have here, this indicates that there's some kind of resonant feature in these spectra. And you see the same kind of thing in the meander. The grouping is ever so slightly less peaky. It's not quite so resonant looking, which is just by virtue of the meander pressure field is very much more confined to the depth of it. But we can get a really nice idea of what's going on when we plot these as a function of distance. So this basically is a plot of the attenuation as a function of distance, and the attenuation here is just given as the magnitude of the cross spectrum between the pressure fluctuations sensed at the two microphones, normalized on the reference spectra of the reference mic. I think the key points on these graphs is that at the fundamental resonant frequency on both surfaces, we appear to be trapping, sustaining, and guiding a surface mode down the system. So as predicted for the slotted surface, we actually get a kind of a wave that looks like it's attenuating as we propagate across this 150 mil. For the meander case, we have a lot less attenuation, and this is due to the difference between the dispersion or the group velocity of the two dispersions. So slotted array, we expect the attenuation to be greater as we approach the fundamental limit of our metasurface cavities. And for the meander array, we don't suffer with the viscous losses, thermoviscous losses so badly. So this is like really, really encouraging. And then you can take the spectral estimation and you can do Fourier analysis in space, and you can actually access the full wave number frequency spectra, just as we would do in our quiescent type measurements. So in both cases, we get reasonable agreement between the results of our FEM model, even for the higher order, higher frequency modes, and the meander, in the meander case, we get very strong features that disperse all the way up to the Brillouin zone. So this basically will form the basis of future acoustic surface wave and flow interactions that we're trying to investigate. To date, what we've done is we've demonstrated the excitation of acoustic surface waves by the turbulence, and we've demonstrated two designs that will that have different features in their dispersion relation that we can use to target a flow application. Where we view this going is to have new metasurfaces with tailored phase speed to match the convective speed of the flow above. So for example, here we've got flow above, this excites a wave, and at some point later downstream we might want to re-influence the flow. Another thing that we might want to do, for example with the slotted array where there's high attenuation, is to pump the cavities and have this wave die off very rapidly and then pump later to absorb some of that energy in the flow. We're doing some work at the moment to assess the rate of power dissipation offered by the slots, to actually look at the acceptance of how much power we accept from the flow and how much of that ends up in the metasurface. We're also doing PIV imaging to assess the effect of the Kevlar cavity on the flow side. And another quite interesting application is to use these slots to target the zero span-wise wave number, which is the one that's responsible for most trailing edge noise. So the coherent scattering along an edge via that zero K3 component. So that's all I wanted to say today. All I left to do is just to acknowledge the contribution from our Exeter colleagues and our collaborators at Virginia Tech, and ONR and DSTL, who have funded the body of work I've presented. So thank you very much for listening.
Excellent, Tim. This was a really nice pedagogical talk. So I welcome everyone in the audience to come forward with this with their questions. I've got many questions actually, but please.